Okay, so this is the sixth video on module theory. Recall that yesterday I was talking about the snake limb. So let me draw the diagram first and then uh, let's do it. So yeah, so for snake lemma you need to have two short exact sequences. So this is say one of the short exact sequences which is maps alpha 1 and beta 1, and you have another such short exact sequence called is alpha 2 and beta 2. When you have these maps in between AI, BI, and CI, F, G, and H. And then, as I said, you can extend this three vertical lines in both top and below. So then you get this is kernel of F, and this is kernel of G, and this is kernel of H, right? And these three are the inclusion map usual. And you have this co-kernel of F, you have this co-kernel of G, and you have this co-kernel of H, right? And in between those kernels, you have this induced map, as I showed yesterday, that these maps do make sense in terms of domains and codomain. And these three are the projection map from E to co-kernel of F and so on. And you have between the co-kernels, you have again the induced maps. And I also showed that these maps also make sense. Okay, so what Snake Lemma tells you is that it guarantees existence of connecting homomorphism between kernel of H, this is, that is from here, and co-kernel of H. So you can get a map using this lemma from here to here, such that we call this map delta. So such that you have this sequence, right? From 0 to kernel F to kernel G to kernel H. From here you go to co-kernel of F via delta. Then again you have this co-kernel of this F, G, and H to 0. So these are your alpha 1 tilde, beta 1 tilde. This is the map delta. This is alpha 2 tilde, and this is beta 2 tilde, right? And this is an exact sequence. So okay. So let's see. So yesterday I've already showed that the exactness at these 2 points and also at these 2 points. So the only thing remaining is to show exactness at this and at co-kernel of it. But to do this, we need to first define what the map delta is, and let's see how to do it. So remember, this is a basic setup such that all these squares are commuting. Right. So this square is commuting, this square is commuting. Yeah. So let's see. So suppose so delta is a map from kernel of each. So let's take any element from there. Let me just change the colors. So let's see how we can do it from the diagram. So for that, okay. So suppose you have any element inside kernel of each. That you can also think as an element of C1, right? Because each is indeed a map from C1 to C2. So anything in kernel of H will so will certainly lie inside C1, right? So let's take any arbitrary element, call it X. So X is here. You can also think X is here. And now because beta 1 is surjective, so these two rows are exact. So this row 1 and row 2 both are exact. So X has a pre-image under uh, beta 1. Let's call it B. So beta 1 of B is X. So X was your chosen point from kernel H. And so B is element of B1. Okay. Now, so you have B here, right? So if we apply beta 1 to it, it will go to X. This is beta 1 of B. So far, so good. Now, if you go down from B, you will get that. Let's see. So we need to go to here. So remember, this is our target. And to go there, at least we need to go up to A2 so that you can use the projection map to go to kernel of. So that's easy. So the main objective is to go to A2. And so far we have reached here. And if we go down here, so we'll get G of B inside B2. But let's see if we can manage to do. So we need to go to alpha 2. That is, we need to find something inside the image of alpha 2 so that we can pull it back from B2 to this A2, right? And so we need to find something inside image of alpha 2. But that is same as finding the element inside kernel of beta 2 because they are the same due to exactness. So let's see if we can do it from this G of B. So if we apply beta to it, then due to commutativity of this square, you will get that. Uh, so this is G, this is beta 2. This is same as acting if you act like beta 1 first and then H. But again, this is 0, right? Because this is X and X is in kernel of it. So we are done. So beta 2 is in image of alpha 2, and so this can be lifted, right? So there exists a pre-image because this is in image. And remember, this A has to be unique because of the fact that alpha 2 is injective, right? So if there is a pre-image, that has to be injective. That has to be unique. So there exists a unique A inside A2 such that this holds. And now it is clear. So this you define this delta of x to be so you are here, right? This is the premium, and that is alpha 2 of a. So just then take the uh, projection of that a plus you have this image of x. This is the definition. So how do you define it? Let me just recall it again. So you take any element of x, you pull it back via beta 1 to go B to get a pre-image inside B1, call it B, and then go down via G, and you see G of B is inside the kernel of beta 2 due to commutativity of that right square. And then you just, because the kernel of beta 2 is same as image of alpha 2, so we can pull it back to A2 and then take the usual projection. So, yeah. But in this step that we have used to define delta, there are two such choices of pre-images, right? Because uh, we choose this B here due to the fact that since beta 1 is on to. Okay. So we need to check if this is well defined or not because we may get more than one pre-image, right? So we need to check if all of those pre-images are going indeed towards this single element. Or in other words, whether this choice of pre-image is like whether this map is independent of the choice of pre-image under beta 1. So this is number one, and again we choose the pre-image here, but that is not going to cause us any worry because of the fact that the uniqueness, since alpha 2 is injected. So here the choice of pre-image is unique, so we don't need to check anything here since alpha 2 is 1 1. Okay, so let's see. So suppose there exists another element. Let's call it, say, suppose x is there, you have the pre-image B, and suppose if possible, or if possible, so suppose because it can be possible, so it's not like there exists exactly one pre-image. So let's say suppose right, so beta prime is another element of B1. Okay. So then what do we need to show? We need to show that both these. Uh, so let's see if we can do the same process using B prime. What do you do? You first take G of B prime, that will be again alpha 2 of some A prime, right? And then this delta of x will be your A prime plus image of. And here it is this. We need to show both of them are same. So same means we need to show that is uh, A minus A prime belongs to the image of A. That is what we need to show, right? Yeah, so if they're like A minus A prime is inside image, so their class will represent the same image. So that is what we are looking to show. So let's see if we can do it somehow. So we are at A minus A prime. We need to check this. But observe one thing. This is like X is both beta 1 of B prime as well as beta 1 of B, right? So this is 0. This will imply beta prime minus B is inside kernel of, sorry, B prime minus B is inside kernel of beta 1. That is same as image of alpha. So we can lift the difference to some point. Let's call it A1. Okay. So let me just remove everything else, otherwise create confusion. Okay, so you have this uh, B prime minus B has a unique preimage again because alpha 1 is injective. So yeah. Okay, so let me write it here. This is your B minus B prime that is being lifted to some element inside capital A1. Let's call it small a1. So you get alpha 1 of A1 minus B. Okay, and now let's see. So we need this, right? So if you just apply G to it, let's see what how far we can go. So if we apply G to it, you will get that this is G of B prime minus B. So yeah, this is G of B prime minus B, and due to commutativity, this G alpha 1 is same as alpha 2 F, right? So alpha 2 F of A1. So you see how we are using this nice commutative diagram to show, because see somehow we have already reached here, right? Because this is the element we are looking to get, right? We are connecting all of them. This is the element inside image of it that we see. So let's see. So this is G of B prime minus B, right? And so now what is G of B prime? This is alpha 2 of A prime, and G of B is alpha 2 of A, and that is same as alpha 2 of this. Now alpha 2 is injective, so you can cancel alpha 2 from the right, and we are done. Yeah, so that is what we needed to show. Exactly. So yeah, so again, so this implies delta is well defined. So whatever pre-image you choose under beta 1, that actually doesn't matter. Okay. So now coming to the main thing. So we have such a connecting homomorphism, and now this entire sequence from 0 to this co-kernel of H is well defined, and the rest of the thing, the only thing that we're left to show is these things. That is, it is uh, exact at kernel of H and co-kernel of F at these two. Okay, so let's see. So let me just show this part first because that is easier part. So let's see. So let me just copy this diagram. Mm, mm, so, so we have this diagram, and so this is the first uh, plane that the so we are showing exactness at here. So that is we need to show that kernel of alpha 2 tilde is same as image of delta. That is what we need to show. And let's see. So take any element from image of delta. So any element would look like delta of x. Right? This is inside image of delta, and let's call it say, a plus a4, or let me call it a2 to emphasize this is inside. Okay. So then remember how we have defined delta. So what you get? You get that. Uh, let's see. So this is inside image of delta. Okay. And remember this a2. Uh, if you apply alpha 2 to it, this will go to g of b 1. Let's say. Where if you apply again beta 1 to b1, you will get x. That is how we define it. Remember. So then that is easy to see, because then what we need to show? We need to show this is inside kernel of alpha 2 tilde. So you just apply alpha 2 tilde to it. You will get alpha 2 of a2, but that is same as g of b1 plus image of g. But that is same as the 0, right? Because this is inside the image and we are done. So a2, this class belongs to kernel of alpha. That is easy. Just we are just using the uh, definition of the function. So this is part one. And for part two, let's just pick any element from the kernel of alpha 2 tilde. So let's see. So any element from kernel of alpha 2 tilde will imply that if you apply alpha 2 tilde, you will get uh, f of a1. Right? So this is same as saying this alpha 2 of a2 is inside. Oh, sorry, this will be inside image of g. So anyway, so if we apply alpha 2 to a2, you will get. So this belongs to image of g, right? And now we are almost there, because then let's see, let's call it g of say b. So there is some premise. So suppose let this g of b. So now remove this. We need to find a pre-image. Remember, we need to show that this a2 plus image of f belongs to the kernel of, sorry, belongs to the image of delta. So you need to find a pre-image. So you need to go right here at this. And so far, let's see. So this is the element a2. Uh, we showed this belongs to g of b. This is same as g of b, so we get here. And now just take the element x to be beta 1 of b, right? Let define x to be this. And then it is easy to see, because see, because b is a pre-image of x under beta 1. So what you do, you take then g of b has a pre-image a2 under alpha 2. That is a unique pre-image due to 1 property. And you just take the class of alpha 2. Right? That is how you define. That is what we needed. So this element indeed a2, the class of a2 belongs to image of delta. So the first claim has been proved, and that is the easier one, or the, let's say it's the shorter one. So yeah. Anyway, so let's show the exactness at the other end. So it's from for here you have to show that kernel of delta. Let's see. So kernel of delta is where? It is inside kernel of H. You have to show this is same as image of beta 1 tilde. Okay. So let's see how we can do it. Okay. So mm, again, let's take any element from beta 1 tilde. Remember, beta 1 tilde is just the map beta 1 with the restriction on the kernel of G. Anyway, so let's take an element beta 1 tilde from image. So we'll call it element beta 1 tilde B1, but that is same as beta 1 of B1. And we to show that goes to 0 under the map delta. We just apply delta. And let's see. So, so remember, we need to show. that this delta of this goes to zero. Zero inside where? Zero inside kernel of H. You need to show this is actually zero inside. So you need to show this belongs to the image of one, right? That is what we need to show. Zero. Okay. So let's see. So mm, we have beta one of B1, the element, and so this is the element beta one of B1. So this obviously has a pre-image, namely B1, and then what will be this G of B1? So G of B1 will then have a pre-image under alpha 2. Okay, and so what is that pre-image? Let's find it. So G of B1, if you apply beta 2 to it, uh, due to commutativity of this square, so beta 2 G is same as H beta 1, right? So H of this. Okay. And so yeah, and that is 0, right? And then because this element is inside kernel of H, and now because so then what you get that G of B1 is inside the image of alpha 2 and uh, the pre-image. So what will be the pre-image? So suppose the pre-image is say some A2. So G of B1 will be alpha 2 of some A2. This is a unique element. And this A2 is indeed the image of this beta 1 of B1 under this map delta. So that is A2 plus the image of F. So indeed the only thing remain to show is that mm the say this A2 belongs to image of say F. That is the only thing remaining. So So let's see how we can do it. So we need to show that this is indeed so that this will give you the zero case. Okay. So let's see. So then um, okay. Let's go back to the diagram. And what you get is say so mm, G of like uh, you have this image as I've written what this beta 1 tilde of B1, right? And oh, I don't need to use all of that actually. Like I don't need to use all of this information because if you just take any beta 1 tilde from image of beta 1 tilde, let's say some element of this form, then clearly G of B1, what will be this? So let's see. So G of B1 from here will be 0, right? And that is the alpha 2 of A2, right? From here. And because alpha 2 is injective because A2 is 0, so which is anyway inside the image of it. So you get delta of this this so this is 0 implies the class of A2 is 0, 0 class. So you get this V1 or let me just write it. This indeed belongs to the kernel. Okay, so you don't need to use all of them. Anyway, so let's do the other way quickly. So this is This will show this input, not the other input. Let's just pick an element from the kernel of say delta. So if x belongs to kernel of delta, you will get delta of x is inside f of a. Similarly, so this will be some this. So again, let me just uh, take diagram here and let's see. Let's, yeah. Okay. So this is A1 is inside A1. So we are here, and we need to show this is inside. Say we need to show this is inside image of beta 1 tilde. So we need to find the pre-image. So we need to go with here. We are here, and so then let's see how we can do it. Again, so if we apply this, and say, so you have x here, and let's just take any pre-image of this is x can be also seen viewed as an element of C1. So you can take a pre-image, call it B. So then you get that this say what should I say here? G of B is here, okay, and it will have a pre-image under alpha 2. Let's call it A2. Yeah, and so this A2 bar is what delta of x. But so just what we do is say suppose so let me just call it B1. Okay. So then you get that x is beta 1 of B1, right? Because you chose pre-image to be B1. And then G of B1 is alpha 2 of, so let's see, alpha 2 of f of a, right? Because delta of x is this. This is just this. And again, if you apply the commutativity of this diagram, you will get that this is G of alpha 1 of A1. So now we have an element from kernel of G, right? And let's see if that can do a job. So this is inside kernel of G. So you find such element inside the domain. Yeah. And if you apply beta 1 tilde to it, let's see where it can take. So that is just beta 1, and beta 1 composed with alpha 1 will give you 0. So and beta 1 of x1 is x. That is so x is in image of beta 1. So that is how you show that this sequence from let me point it out here. So that sequence from here to here via this snake map or the connecting map delta is indeed an exact sequence. So yeah, so that is what we get from here. And I've already discussed the usefulness of this lemma in homology theory.